Hello all. So in this session we are going to start with module 4 of instrumentation systems. So these are the various topics we have to cover in this module. Dynamic testing of pressure measuring systems, high pressure measurement, low pressure measurement, sound measurement and flow measurement. So let us first move on to dynamic testing of pressure measuring system. In order to determine the regions of accuracy of theoretical predictions, or in order to find numerical values of system dynamic characteristic, we need to modify the experimental testing methods. That is, we need to include some more tests into this experimental testing setup. So the test that we are including in experimental testing in order to determine the numerical values of dynamic characteristic, such tests are known as dynamic test. So various type of dynamic testing methods are step function test, impulse test and frequency response test. So first one, step function test. These tests can be classified into different types depending upon the natural frequency of the system. So for frequencies which is less than or equal to 1000 Hz, then the devices in which were the bursting of thin diaphragm subjected to a gas pressure is done. In this case, a general rule must be followed during this type of testing method, step testing. That is, during the method in which bursting of a thin diaphragm which is subjected to gas pressure is done. In that case, we should follow a general rule. That is, the rise time of the step function. Step function, in step function test, we will use a step signal. So that step signal will be having the rise time, the end time, similarly the operation time. So the rise time of the step function must be less than about 1/4 of the natural period. Natural period is 1000 Hz or below. Okay, so whatever be the period, natural period of that particular system, that will be the, for example, for a 1000 Hz system, the step function rise time must be 0.25 millisecond or less. Okay, so this rule should be followed if you are employing the system in which the bursting of a thin diaphragm is done. This is a figure showing the step function procedure. That is, here is a plastic diaphragm, which is the thin diaphragm, and this is the transducer diaphragm. Here, the pressure of this area is P1 and this area, this small area, is P2. The volume containing P2 is smaller than that containing P1. Thus, when the thin plastic diaphragm is ruptured by the solenoid actuated knife, that is this one, then the pressure P2, this pressure in this small volume, will get rises to pressure P1 quickly. When this plastic diaphragm ruptures, the P2 will increase to P1. If a decreasing step function is needed, then P2 can be made larger than P1. Okay. Now, the rise time of about 20 microseconds can be achieved in Arsenal dynamic calibrator, and in this device there is a quick opening poppet valve between high pressure chamber and low pressure chamber. I will show you the figure of that Arsenal dynamic calibrator. So this is the Arsenal dynamic calibrator, and in this figure, this one is the poppet valve. This one is the poppet valve between the high pressure and low pressure chamber. So this poppet valve, or the quick opening of the poppet valve, it will open and close, and during this opening and closing, then high value of positive and negative gas pressures will be formed. So also during, if you are using such step function test apparatus, that is Arsenal dynamic calibrated, extremely fast rise time is obtained by keeping the volume of transducer chamber very small and by using a simple flat face puppet valve, then obtain extremely fast rising time. And in that case the valve is opened by, that is in case of flat face puppet valve, the opening is obtained by the impact of a falling weight. Okay, so that is about step function test. And now for system natural frequencies which is greater than 1000 Hz, shock tubes are used, and by which sufficiently short rising times can be obtained for step function. So what is shock tube? This one in this figure you can see, this one is the shock tube, and here this is the high pressure end, this is the low pressure end, and this is the diaphragm which we need to burst. Okay, so here what happens, what is the principle of this thing? As I told, that diaphragm, it is a thin diaphragm that separates the high pressure and low pressure chambers, and the transducer to be tested is mounted flush with the end of the low pressure chamber. And that is at this end, this end of the low pressure chamber, we are mounting the transducer which is flush mounted to this. So what will happen when this diaphragm is burst? At that time a shock wave will form. A shock wave will be formed, and this shock wave will travel towards the low pressure end at a speed that may greatly exceed the speed of the sound, and at the same time a rarefaction wave will travels from the diaphragm towards the high pressure end. That is, when this diaphragm bursts, a shock wave will travel towards this end, transducer end, and the rarefaction end of that wave will travel towards the high pressure end. So in the system, the transducer is thus exposed to a very sharp pressure rise which is maintained constant for a short interval before various reflected waves arises as a noise. Okay, so this sharp pressure wave, we need to maintain it for short interval for analyzing. Otherwise some other reflected waves due to the rupture may also come towards the transducer, to affect the transducer. So the transducer will get confused which is the pressure wave which we need to test. Okay, so due to that we need to maintain this pressure wave which is about 10⁻⁸ seconds, then for a short duration, in order to stop all other reflected waves. So this length of this interval may be controlled to certain extent by proper proportioning and operation of shock tube. So that is all about step function test. Next one, impulse test method. A simple impulse test method, it is applicable to flat flush diaphragm transducers, and it utilizes a small steel ball dropped onto the diaphragm. The impact of this dropping of the ball onto the diaphragm, it will excite natural oscillations, and these oscillations are then recorded and analyzed for natural frequency and damping ratio. Another impulse method employs the shock wave created by discharging 25,000 volt across a spark gap. So this is one method of impulse testing method, and this is another method. Okay, so at first method we are dropping a small steel ball onto the diaphragm and creating shock waves, and in another method we are discharging at 25 volt across a spark gap in order to create shock wave. Okay, in this case the spark gap and the transducer are located about 3 in apart in open air. So here a pressure impulse of 0.2 microsecond rise time and 100 lb bar inch square peak can be obtained. Okay, in this type of impulse test method. So next one, frequency response test. This figure shows the method of constructing a frequency response tester using liquid as the pressure medium. Okay, so here this is the flexible diaphragm, and this is the reference transducer, and this is test transducer, and this is constant bias air pressure. And here in this part you can see an electrodynamic shaker for creating the pulses. So the vibration shaker applies a sinusoidal force of adjustable frequency and an amplitude to the piston or diaphragm to create sinusoidal pressure in the fluid filled chamber. So such vibration shakers, or the device here, the electromagnetic shaker, these are readily available in industry, and it will cover a wide range of force and frequency as per our requirement. The average pressure about which force oscillations takes place may be adjusted by regulating the bias pressure on the air side of the cylinder. So as the frequency or amplitude is varying, a reference transducer need to be mounted at a location where it will experience the same pressure as the transducer under test. In this figure you can see a reference transducer is there. It is located at the same section so that it also experiences the same pressure as by the test transducer. Okay, so this reference transducer must have a non-flat frequency response beyond any frequencies to be tested, and this flat frequency response of the reference transducer can be determined by some independent method such as shock tube, which I have discussed just before. In testing another transducer, one merely calculates the amplitude ratio and phase shift between the reference and test transducer. So in order to test another transducer, we should calculate the amplitude ratio and phase shift between the reference and test transducer, and then we can determine the test transducer frequency response. Okay, so these are the various testing methods, dynamic testing methods for pressure measurement. Next let us move on to high pressure measurement techniques. So high pressure means pressures which are of a very high value. Pressures up to 100,000 pounds per inch square inch, pounds per square inch, can be measured easily with a strain gauge pressure cells or Bourdon tubes. Okay, so up to this pressure, up to this much value, then the pressure measurement device can be this tube, that is strain gauge pressure cells or Bourdon tubes. So here I have given what is this pound per square inch. It is also a unit of this pressure measurement, so you can read this out. Now Bourdon tubes. Bourdon tubes of such high pressures have nearly circular cross sections, and thus it will give a little output motion per turn. That is, in the Bourdon tube, input is pressure and output is changes in displacement, changes in length. Okay, so the output elongation or displacement is proportional to input pressure. That is the functioning of Bourdon tube. Okay, so in Bourdon tube of such high pressures, if we need to get a measurable output, then helical form with many turns is generally used. So I have told in previous videos, the Bourdon tubes have many different type of structures, and like helical form, like circular cross section, so different forms are there. So in Bourdon tubes that for Bourdon tube, if you are using for high pressures, then helical form will be more good. Next one, strain gauge pressure cells. This can be temperature compensated to give a 0.25% error over large temperature range. So these conditions should be followed if you are using strain gauge pressure cells. Now, if the fluid pressures is above this 100,000 pounds per square inch, then electrical gauges based on resistance of manganese or gold chrome wire with hydrostatic pressure are generally utilized. The sensitive wire is wound in a loose coil, and one end of which is grounded to cell body and the other end brought out through a suitable insulator. So the figure of which is given here. So this is a sensitive wire. In the center portion you can see a wire. So one end of it is connected or grounded to the cell body, okay, and the other end is brought out through a suitable insulator. The coil is enclosed in a flexible kerosene-filled bellows, which transmits the measured pressure to the coil. So this is the bellow here, and this is the kerosene inside a kerosene you can see, and this will transmit the input pressure, okay, to the coil. Coil, you can see there is a coil surrounding the wire, thin wire, okay. So this kerosene filled bellow will transmit the input pressure towards the coil. So in this coil or in this wire, that is a thin wire, we will obtain resistance changes, which is the output of this device. And by measuring this output resistance changes, we can obtain the pressure input. Also, by which method we will determine this resistance change? We can use any conventional method such as Wheatstone bridge methods. So the measurement of local contact pressures between rolling element in gears, cams and bearings may be accomplished by depositing a thin strip of manganese or gold chrome onto the surface as a pressure transducer. So that is about this high pressure measurement technique. So this is a device for measuring high pressure transducer whose working is just I have explained now. Next, let us move on to low pressure measurement. Thank you.